And so I'm going to start with disclosures. And I have a very strong disclosure because I did my PhD with one of these companies in computer science. So we all know that 3D planning improves accuracy. We all know now that 3D CT scans is the gold standard to determine glenoid anatomy. So it is necessary to have a 3D CT scan preoperatively. It has been proven, and it's going to be shown by Philippe in the next talk, that standard instruments and 3D planning are better than standard instruments and 2D planning and no planning at all, of course. And this has been proven in TSA in vitro, TSA in vivo, and RSA in vivo. So it's pretty clear now. So what does the software do? The software first is going to recreate the humerus and the scapula in 3D, reconstruct the bones and label them, not only have a 3D image, but identify which is which. Then you need to identify all these measurements that Peter presented, and for this we need reference planes, and this is where the software differ a little bit, and this is what I'm going to try and clarify in this talk. In order to obtain glenoid version, inclination, and subluxation, then most softwares, they allow you to virtually implant the arthroplasty, and so determine reaming, glenoid humeral implant positioning, bone graft, assess lateralization, distalization, and some softwares allow you to have a simulation, and again, as we've seen, simulation is not very precise for now because it's only passive, it doesn't take into account soft tissue, and it's only glenohumeral. We have no idea what's going on the scapulothoracic joint. So as you can see, every company has their own little software now, and there are a few comparative studies in the literature right now, so it's very easy actually to answer these questions because 3 studies have looked at this. And so when we look at these 3 studies, well, we see that there is considerable variability between softwares, that Blueprint has a version that significantly overestimates version. But then what is the truth? Is Blueprint overestimates or the other underestimate? We don't really know. And then inclination do not really differ between software. And so why did I say why some overestimate, why some underestimate? Because it has not really any sense to say that one is better than the other. It's like saying that miles per hour is better than kilometers per hour. They measure the same thing, but in a different way. So you just need to understand how they measure, what is normal with the software, what is pathologic, how it is calculated, and then to know if the method has been validated or no. And so how do they work? So they all work the same way, but then differently in each step. So the first step is to have the 3D segmentation. Then you need to have a glenoid plane, a scapular plane, a transverse axis, and the humeral subluxation. And so the 3D segmentation, what is that? The 3D segmentation is what allows you to transform a volume of 2D images into a 3D model. And this can be manual, semi-automated, or fully automated. So manual, it's very time consuming. No one does that. It's just contouring manually the scapula, and you say this is the scapula. You contour manually the humerus. You say this is the humerus. And now you have 2 bones that have been fully manually segmented. You can do it semi-automated, and that's what is used mostly. And this is the more widespread method, which is quite easy. You need to first set a threshold, and you tell the machine, okay, this threshold of intensity is bone. And so as you can see on the picture on the right, all the bone has been identified. And then you can manually select the humerus, and you tell the machine this is the humerus, and manually select the scapula, and you tell this is the scapula, remove the rest. And sometimes you need to help the machine to manually separate scapula from humerus in cases of severe arthritis. And then it can be fully automated, and there are 2 methods that exist today to fully automate segmentation. Either use a statistical shape model, so feed the machine with many different 3D CT scans, so the machine can build a statistical model of a shape of the scapula, or more modern techniques that rely on machine learning that are quite efficient too. Then you need to set the glenoid plane. The glenoid plane is necessary if you want to determine glenoid version and inclination. So the glenoid plane, again, several methods. The first method is manual selection of anatomic landmarks. So you pick manually, it's an engineer typically who does that. You pick 3 points among the 4 points that are here, those superior, inferior, anterior, and posterior points of the glenoid. Or you can use an automated selection of the glenoid face surface points. So the machine identifies all the points, a cloud of points on the surface of the scapula, and then it's going to be able to determine the best fit plane. Or you can use the same method, but instead of determining the best fit plane, you can use the best fit sphere, which may seem a little bit more logical for a surface that is concave and not completely plane, even though some surgeons try to make it completely plane when they ream. Then you have to determine the scapular plane. So we had the glenoid plane, now we need the scapular plane to determine the glenoid version and inclination also. So then again, you can either select manually the landmarks, and you can select 3 anatomical landmarks that have been described, the glenoid center, and again, several methods to determine where is the glenoid center, because it's not that easy. So you can use the same 4 points as we've seen before, and it's the intersection of these points. Or you can have a machine look for the best fit circle that matches the inferior part of the glenoid, and the center of that best fit circle can be considered the center of the glenoid. Or you can have a cloud of points again and determine the centroid of this cloud of points. Then the second point is the intersection of the scapular spine and the medial border, and that's called the trigonum scapulae. And this is a point that is not very easy to pick. It is a large point, and sometimes there is quite some imprecision in this point. And then the most inferior point of the scapular body. You can either also select manually 10 landmark points that are different from these 3. This has been described by a team in Lausanne, and you can choose 5 points from the supraspinatus fossa and 5 points from the axillary border of the scapula. And these points have been found to be quite reliable and reproducible, and this helps you to determine the plane of the scapula. Or you can use a completely automated method. Oops. Can I run the video? Yeah, it's running. It's a completely automated method. So you have a cloud of points from the scapular body, and then automatically the machine is going to determine the best fit plane that matches all these points from the scapular body. Then you need the transverse axis to determine glenoid inclination. Then again, several methods. You can use the line that we've seen before, the line between the center of the glenoid to the trigonum scapulae. So this is called the CG line, but the CG line is not very precise because of this trigonum scapulae that is difficult to determine. The center of rotation, the center of the glenoid can be determined through these 3 methods that we've seen. You can use the 5 landmark points along the supraspinatus fossa that we've seen previously as the transverse axis, or you can use a completely automated method that is going to identify automatically the intersection points between the 3 branches of the Y, so the spine, the coracoid process, and the axillary pillar. And the intersection of these points is going to be a line, and you can find the best fit line, and this can give you automatically a transverse axis. And then to determine version and inclination, you have again different methods. So you have your planes, but now you need to compare these planes to determine version and inclination. So either you look at the difference between planes, so the version can be the version of the glenoid plane relative to the scapular plane. The inclination is that of the glenoid plane relative to the transverse axis. So difference between planes, but you can also use the best fit sphere that we've seen. And again, for a concave surface, maybe this is more appropriate. And for the version, it is the angle between the scapular plane and what we call the glenoid best fit sphere center line. So it's that red line that you can see here. It's the line between the center of that yellow sphere, which is the best fit sphere, and the glenoid center point. It's a vector. And so you have a difference between the scapular plane and the vector for version, and same thing for inclination. Then for humeral head subluxation, again, 3 methods have been shown. The first one is to determine the humeral head by manually selecting 5 points on the humeral head, or you can identify the head automatically by calculating, automatically identifying the best fit sphere that fits the non-eroded segments of the articular humeral surface, as you can see on that picture. Then you have identified the glenoid on one side, the scapula on one side, and then the humerus on the other side. Then you need to determine subluxation, and either you use the sum of the humeral head radius, so the distance that you can see here, plus the posterior offset relative to the scapular plane. So this is the subluxation of the humerus relative to the scapular plane. Some have proposed to do the same thing but relative to the glenoid plane, which makes a little bit less sense. And some propose to use the scapular plane and to calculate the volume of the humeral head that is on the side of each, either anterior or posterior to that scapular plane. So let's go back to the literature and the articles that are cited usually. So this is the article that says that this method is the best because compared to a cadaveric study, this is a method that found perfect reliability. But again, it's logical because on the cadaveric study, they used exactly the same points. So if you use the same points, they just show that a CT scan is reliable. They're not showing anything about the method. Then, if you look precisely at literature, you can see that there are many mistakes. I'm not going to go into this in detail, but we've seen that Blueprint uses a best fit sphere instead of a plane, and here they mention that it's a difference between planes, so nothing is very accurate, and I think it's important to have things clear if you want to understand what you're doing. And then when you look at this study that compared several methods, well, they compared Blueprint to 3 other softwares, but VIP, Materialize, and Exatech, they use exactly the same methods with manual selection of glenoid landmarks, scapular landmarks, CG line, and humeral head landmarks. So if you use the same method, globally, you're going to find the same results. And then if you use another method, you're going to find other results. Which is best? I have no idea. It's for you to judge which one you feel more comfortable with. But there is no point in comparing these methods because they show different information. And Blueprint is going to give automated selection of the glenoid best fit sphere, scapular best fit plane, the Y intersection of the best fit line, and the humeral best fit sphere. So what are the advantages of a manual technique? Well, an engineer has to subtract the humerus from the glenoid, so it takes some time, but then sometimes it can be more precise. As you can see on the B picture, this has been done automatically without the help of an engineer, and too much of the glenoid has been removed, but the engineer has to place the landmark, so it takes time, and you cannot do it on your own. And also, he places the landmark, and this is a study that has been done by a French group, and you can see that these blue dots are the imprecision of each landmark. And you can see that the trigonum scapulae is a very big blue dot because there is a very big margin of error. So all the measurements rely on this big blue dot that is not very precise. Automated technique, of course, you do automated subtraction of the humerus, so you can have some problems with that, but all the measures are completely automated, so it's quick, there's no engineer, and it's more reproducible. Then what about the future? The problem is that now we can plan, we have very good software to plan, but we don't know what to plan for. And when we ask surgeons where they should plan, you can see that there's, even in the entry point in the glenoid, there's very big variations, and no one knows really how much version, how much inclination, and where we should put our implants. So maybe, as JP has mentioned before, maybe AI and machine learning is going to help us in the future to predict outcome, to predict the type of implant that is needed, and to predict the position of the implant. But also that something has been introduced by Professor McFarland is that this software, they don't have at all the soft tissue, and so that was the objective of my PhD. It was to include soft tissue in the software, and so now we have the possibility to automatically reconstruct, so not only the bone, as you all know, but also the muscles, as you can see here, and have a precise evaluation of fatty infiltration, muscle volume. So this is the first step. Then we need to animate this to see how these muscles contract. But right now we already have the 3D shape of the volume and the 3D fatty infiltration in an automated, a completely objective manner. And then the last point is the scapulothoracic motion. We need to include that later because right now we're planning on the shoulder like this. So we know that there is some retroversion. We can put a graft or remit flat, whatever you choose. But then you place your base plate, you place your humerus in a certain amount of retroversion to match your base plate. But if you look at the whole picture, if you look at where your scapula lies on your thorax, maybe it's not in this position, maybe it's very kyphotic, and maybe it's like this. And then if you put your humerus in the same position, you're going to have impingement very soon, either in internal or external rotation. So all this needs to be included in our future thought process. Thank you very much.